Hello, everyone. I'm Corwin.
I'm Sylvain.
Today, we're going to be talking about how to train a model on GPUs efficiently. So can I get a show of hands of who has used a machine learning model before? Great. If you haven't used a machine learning model before, I'd highly recommend you going to check out one of the many ones available. There's Claude, there's ChatGPT, DeepSeek. Definitely recommend to boost your workflow. But I guess maybe the better question is, who has trained a machine learning model before? OK, all right, still a good number of hands. What about trained a machine learning model using a GPU? OK, so maybe I don't actually need to give this talk. Seems like you guys already know everything that's going on. But we can still talk a little bit about it. So I guess the first question is, like, why would you want to use a GPU? I mean, we have CPUs. CPUs are great. They're what we've been using forever. At Jane Street, CPUs are really good for our trading systems. They have very good sequential performance, very low latency, a decent number of cores nowadays, a decent number of threads per core, one or two. And they do that sequential programming extremely fast. GPUs, on the other hand, are just extremely parallelizable and have a lot of throughput. To sort of illustrate that point, what do you guys think? How long does it take to do one floating point operation on a GPU versus a CPU? Anyone have any ideas? How long does it take to do one floating point operation on a CPU? Yeah. So a nanosecond. That's approximately right. What about on a GPU? Anyone have any ideas? Yeah.
2 nanoseconds.
2 nanoseconds sounds like a good answer, but actually GPUs are really slow at doing one floating point operation. It's around a microsecond. So this is a little bit tongue-in-cheek, because doing one floating point operation is never a thing that you'd actually want to do on a GPU. But this is 1,000x difference. CPUs are 1,000 times faster than GPUs. Why would we use a GPU ever? And the answer is the parallelism. So in doing machine learning, a thing that you often want to do is matrix multiplication. And matrix multiplication is an operation that is highly parallelizable. You can split up the work entirely, so each thread can sort of deal with only one of the output elements of your matrix entirely independently from all the other threads. And this massive parallelism enables the GPU to do computation extremely quickly. So for doing 2048 by 2048 matrix multiplication, how long do you think this takes on a GPU versus a CPU? Anyone have any guesses? Yeah.
I don't know, maybe a second on the CPU?
A second on the CPU. So CPUs are actually a little bit faster than that. That is a good ballpark estimate, but there is stuff like SIMD and multiple cores on the CPU that enable us to sort of get some parallelism. And then it's actually 28 milliseconds. And then if you think about the GPU, it's 200 microseconds. So before we had 1,000x faster on the CPU side, now we're 100x faster on the GPU side. So this is kind of just absurd. The GPU is getting so much speed up for doing this matrix multiplication. And that's why we want to use the GPUs. They have this massive parallelism. They enable us to do this amazing computation that we need, and that's why we want to use them. So over in this talk, first thing we're going to talk about is how to use GPUs to train neural net models. And then we're going to talk about removing the bottlenecks in doing that training. And then finally, we're going to dive a little bit lower level and understand the GPU kernel operations that we do and how to optimize those as well. So I'll hand it over to Sylvain to talk about neural net training.
Thanks. And yeah, maybe to get a sense of how familiar you are with this diagram, can you tell me, with a show of hands, does this make sense or not at all? Just so that I know how much time I should spend on that slide. Please raise your hand if it makes sense. OK, kind of. So maybe I'll go a little bit over it, but quickly. So when you train a machine learning model, you do something that looks like this. Mainly, you have some data, usually that comes in the form of some inputs and some desired outputs for your model, and you feed them through your model. From the output of your model, you compare them with what you expected, the targets that you had in your data, and you compute a loss, which tells you how wrong your model is. If you're at the start of training, your model is going to be very wrong because it's been randomly initialized. And then you compute the derivative of that loss with respect to every parameter of your model, which gives you the gradients. And we do this because as an analogy, if we're at the top of a mountain and we want to go to the bottom, we only need to take a step in the downward direction. And this downward direction is going to be given to us by the gradients. Once we have those gradients, we take that little step in the direction of the gradients to make our model a tiny bit better, and we rinse and repeat the whole process thousands, if not millions of times, until we have a model that's trained and outputs sensible results. And to do this, we usually use PyTorch here at Jane Street, which is a deep learning framework that is very good for two things. One, it provides us with GPU kernels, so we will be able to execute all of those operations on the GPU and leverage that high parallelism. And two, it comes with the automatic differentiation. So like the diagram that we had before looks like this in PyTorch. This is like the data part. We iterate through some stream, which is called a data loader in PyTorch, that gives us those inputs and targets. We compute the outputs of our model on the batch of inputs, and then a loss from this thing. And during those two operations, we execute potentially a lot of matmols, leveraging the power of the GPU. PyTorch gives us the gradients kind of automatically. We just have to call this magic incantation loss.backward to have them be computed for us. We don't have to manually code like the derivative of every operation we just did. And then we take that little step in the right direction that's going to make our model better. And I just added like some stuff to basically like compute some metrics to figure out how good our model is, and then like print the final value once the training is done. And then, so this doesn't use the GPU for now, but if you want to use the GPU in PyTorch, it's actually very easy. You just have to add a couple of lines here and there, basically like those .2 CUDA kind of everywhere. This is called 2 CUDA because like when PyTorch was first created, like it only supported NVIDIA GPUs, and CUDA is the name of the programming language that's proprietary at NVIDIA to program GPUs. Now PyTorch supports many kinds of GPUs, but they didn't update this specific API, so sorry, AMD. So you move your model to the GPU, you move your inputs and targets to the GPU, then all of the heavy computation that we saw before, so the forward of the model and the backward of the model, where you have lots of matmols, you use the GPU for that. And at the very end, we move back our outputs and targets to the CPU to be able to compute our metrics. And so yeah, we'll now take a deep dive into like what's actually happening behind the scene when we execute that code in PyTorch to understand like where the bottlenecks might appear. And I'll lead back over to Corwin to go over this.
Right, so CPU, GPU pipeline, we want to understand what the GPU is doing when we're running kernels in PyTorch. So to do that, we'll look at a little bit of a simpler piece of code just to make it easier to understand what's going on. So first, we're going to execute this getting data operation, and that runs on the CPU because we're getting data from using the CPU to compute some stuff. Then we'll send that data over to the GPU, and this operation occurs on both the CPU and the GPU because the CPU is sending the data and the GPU is receiving that data. And so you can see here on the pipeline, we'll like put an operation on both the CPU and the GPU lines. After that, we'll run a kernel. So a kernel is kind of like a function that does one operation on the GPU. And so you might expect that this kernel only executes on the GPU side because it's a GPU operation. But in fact, it needs to be run on the CPU as well. So the CPU does some computation to figure out the launch parameters and then communicates that to the driver. And then the driver tells the GPU, please execute this operation. And then the GPU actually does the execution. So all of the kernels take place on both the CPU and the GPU. So after we do this linear layer, which is a matrix multiplication, we then move on to ReLU. ReLU is just another operation. You don't really need to know what it means. It's just another thing that is a kernel that is launched on the GPU. And finally, we can go back and get data again and send that data and then do some more layers. So if you look at the GPU line, you'll notice that there are a lot of gaps. And that is bad. All of the time that the GPU is not doing work, you're like burning money. Because GPUs are super expensive. You want to keep them as full as possible. And so this huge set of gaps is like really embarrassing. Fortunately, I just lied to you. This is not how PyTorch works. What happens is there's this pipeline. So the GPU and the CPU are executing at different times. So going back to our linear layer, the CPU tells the GPU, please launch this operation. And then the CPU can just continue executing while the GPU runs that operation like asynchronously. And so immediately the CPU can continue on and hit the ReLU operation. And I think we'll need to click the mouse to remove that. Perfect. So it'll run the ReLU operation, and that will get launched on the GPU side. And you'll notice because the GPU is still running the linear layer, we will not actually start the execution of the ReLU at that time. the ReLU is queued up. There's a big queue of operations that the GPU is waiting to execute. And so the GPU will just pull things off that queue whenever it's ready. But when we launch the ReLU, we don't immediately start it on the GPU. Instead, we can continue executing on the CPU side, going back to the get data. And then eventually, the linear layer on the GPU side finishes, and we'll be able to launch the ReLU. And we can continue on, so on and so forth. And you'll notice that there are no more gaps between the kernels. We've eliminated a huge amount of inefficiency when we're not doing any work. And this is great. This is a much more reasonable way of doing the GPU work. And in particular, what this allows us to do is it allows us to sort of hide the extra computation of the get data. No longer does that get data need to occupy space on the GPU line because we've overlapped it with the kernels that the GPU is executing. Great. So we can look at what this looks like in the profiler. So this is the Insight Systems profiler from NVIDIA. And you can see the CUDA API line describes all the things that are happening on the CPU to launch kernels. And then you can see in the CUDA hardware line the kernels that are actually being launched. And you'll see the correspondence between the launching of the kernel and the kernel being run. And so you can see that the GPU is far behind the CPU and the CPU is far ahead. And this is basically the behavior that we want. So the thing that you're trying to do when you're executing a GPU program is you're trying to keep the blue bar at the top in the CUDA hardware line full. If your blue bar is not full, your GPU is not being efficient. And so the first step when you're trying to think about stuff is figure out how to keep the blue bar full. One thing that sort of gets in our way is, usually when you're doing a computation on the GPU, you want to actually know what that computation did. To do that, you need to copy data back from the GPU to the CPU. Unfortunately, this synchronization point, where you copy data from the GPU to the CPU, causes your pipeline to stall. So you can see here, we're doing this output.cpu to get the results back. And our CPU is not able to launch more kernels while it's waiting for the GPU to execute. And so that flushes the pipeline. And that causes us to have really bad performance. So in the profile, you can see this GPU sync is causing the CPU to stall. And this stall takes so long to wait for the GPU to finish, that's just completely off the screen. So going back to this diagram, you can see we stalled a really long time to wait for this copy to happen. And then that means that the get data, which used to be covered up by the asynchronous launching of the GPU kernels, is now exposed on the GPU line. And so you have that time where you're getting data that makes your GPU just wait. And this is wasted compute. You're wasting money. You don't want to do that. OK, before I continue on, does anyone have any questions about how this works?
Why does the CPU
Wait, hang on. Can you throw it into the mic? Yeah,
Why does the CPU have to wait for the GPU2 to finish before it issues the lin instruction?
That's a good question, and we will talk about that later on. But it's some complex details of how the copying actually happens. Any other questions? Cool. OK, so going back to the profile, we can see that synchronizing took a long time. And then you can see immediately after the synchronized finishes, we have the gap on the GPU side. Looking at that CUDA hardware line, you'll see that gap in the blue line, which means that we're not efficient. So synchronizing, bad. So the question here is, we had this code that we're using to do our training loop. Anyone have any ideas where the synchronizations are?
It'll be at the dot CPU calls at metrics accumulate.
Yeah, that's a great one. So yes, we have a synchronization. This one is, this .cpu sort of makes it clear to you what's going on. We don't want to do that. Any other ideas what synchronizations are? Yeah.
When it's calculating isNAN?
Where it's calculating isNAN. That's a great point. And this one is a little bit sneakier. It doesn't say .cpu anywhere. So you're like, why is it synchronizing? Well, what's happening here is that in order to run the if statement, we need to know what the value of the tensor is. In particular, when you're doing the conversion from the .isNAN tensor into a Boolean, that's where the synchronization happens. And that is super pernicious because .isNAN doesn't cause a synchronization. It's the if that causes a synchronization. And so this is one of the things that when you're writing PyTorch code, you ought to be really careful about and make sure you're checking for any tensor coercions because those are places where you're going to have accidental synchronizations. OK, any ideas for the last synchronization? Or maybe there's more than just one. I know of one. Yeah. Sorry, can you use the mic?
When you step your optimizer, you'd have to like reload your weights onto the GPU to do your next cycle. So there's probably some synchronization that needs to happen.
So that's a good idea. But I think PyTorch is like a little bit smarter than that. It doesn't need you to reload the weights on the GPU every step. The weights are just stored on the GPU, and they remain on the GPU. So, and the optimizer is a bunch of kernels that also just run on the GPU. So in fact, like this is like a good non-example of like of a synchronization where, in fact, operations that you might think need to occur on the CPU side are actually just like launching a whole bunch of kernels. And so like they do occur on the CPU side to launch those kernels, but the actual execution and the storage of the data is all held on the GPU, so we don't need any syncs. Any other ideas? You guys actually spotted this last one earlier. So this copying of the data from the CPU to the GPU, you would think, wait, but that's like the correct direction. CPU to GPU is the direction we're launching stuff in. Why do we need to worry about that? And this is like some details of how the memory copying works. So when you think about what is the GPU doing in order to do this copy, like you have some data on the CPU, and you're sending it to the GPU. But what happens if the kernel decides to swap out the page containing that data on the CPU? Or if the kernel, or if like in Python, we decide to deallocate the tensor that contains that data. Like all of these would be really bad, and then the GPU would be like trying to read memory that no longer points to the right thing. And so what we have to do is we have to wait on the CPU side for the GPU to actually have finished doing the copying before we can continue executing, because we have to hold that memory in place while the GPU is copying it into GPU memory. So this is like not entirely true. For like very small tensors, you're able to do the copy entirely asynchronously, where you just like squeeze the little data inside of the buffer. So like if you have like one number and you copy it, it'll just like fit inside the buffer, and so like no synchronization needs to happen. But for like most things that you're trying to copy from the CPU to the GPU, you need to have a synchronization in the way the code is currently written in order to like keep that data around. Okay, so one thing is that synchronization is not always so bad. Like if immediately after finishing your synchronization, you start launching kernels again, you're not going to wait that long. You're only going to wait like a millisecond. And so if your training loop takes like 1 second to execute, that's like 10 bips of inefficiency. So it's like not too bad. So not all synchronizations are bad, but some synchronizations are really bad. So this is an example of the CPU sync at the end of the loop. And right after we do that CPU sync, we do the work to get the next batch of data. And that work of getting the next batch of data is really expensive. And so that takes a huge amount of time on the GPU side to get that data, even though the GPU should have been doing work for like a previous batch while we were getting the next batch. And so this synchronization is extremely bad because it makes us not be able to do the overlap of CPU work and GPU work. And so you really want to avoid these synchronizations. OK, so how do we fix this? Well, to fix the first synchronization of copying the data back to the CPU to do the metrics, all we need to do is just not do the metrics on the CPU. We can just have the metrics be computed instead using kernels. And then only at the very end of our loop, when we actually need the metrics, do we send them back and do that copy. And what this allows us to do is like avoid doing the copy on the hot loop of the training loop, and instead only do it like rarely. For the next one, we can just compute the loss asynchronously. So instead of having the loss be like, we can check whether the loss is NaN asynchronously. So instead of like blocking the main loop, waiting for the loss is NaN check to run, we do the loss is NaN check and eventually stop the loop at some point in the future. So this does change the behavior of our code, but like if the loss was NaN, the training is going to blow up anyway. And so we're doing like a little bit of extra useless work, but like in the grand scheme of things, we made our training loop so much faster by skipping the synchronization that the like extra work that we did at the end when our training did blow up is just like not as big of a deal. And so this is like a great way. You just want to do all these checks to like make sure things are stable, like sort of in an asynchronous background fashion as much as you can. OK, so the last one, copying the data from the GPU to the CPU. Well, yeah, people thought about this. They're like, this copying it should be done asynchronously. And so the main thing that you need to do to make that happen is you need to tell all of the various systems on the CPU side that this memory should not move. So that's what this pin memory does. So you tell the tensor, you say, put it in a place and make sure that we don't swap it out to disk. We don't deallocate the tensor. We just leave the memory there. And so the GPU can do DMA, which stands for direct memory access. It basically means the GPU can like reach into the CPU memory, grab the data out, pull it back into GPU memory without the CPU being involved. And because we've pinned it into a particular place, we know that it's not going to move. We know it's not going to be deallocated. And so then it's safe to have this be done asynchronously by the GPU. And so the last thing is you need to pass this non-blocking equals true to the copy, because a thing that you could do if you didn't pass non-blocking equals true is you could go in and like mess with the memory. Like you pin it to a particular place and you say it's not going to be moved, it's not going to be copied, it's not going to be swapped out. But like you yourself could go and then touch it and say like and change the values. And this is what would be like some non-determinism execution. And so non-blocking equals true says like I know what I'm doing. I am not going to mess with the memory after I've started the copy. And that's basically what it's like a promise to say that you know what you're doing. Cool. Anyone have any questions about how we fixed all these synchronizations? Yeah, question? You pass the.
So what does check isNAN async actually do then? Will it still like break out of the loop?
Yeah, so that's a good question. So there's a bunch of different things that you can do. One thing is you could have like another thread on the CPU side be like waiting for the copy from the GPU to the CPU. And so like your main thread can continue launching kernels while that other thread is the one waiting for the copy to finish. So that's like one technique. You could also do it using a pipeline mechanism where you are copying stuff. But basic point is you don't want to have the main thread stalled waiting for the copy to finish.
Right, and then the other thread that does the check will preempt like your thread?
Yeah, just like kill the whole process.
Oh, okay, makes sense.
Yeah. Like I think if you want to do something intelligent with the data and like affect the behavior of the main thread in some way that's not just killing it, then like you need to do some complicated like pipeline or like inter-thread communication with like shared memory or something. But if all you're doing is killing the process, like you're just like raising. Cool. So now that we've fixed all the problems, we see this beautiful blue bar with no synchronizations in our profile. And well, I mean, almost. There's no synchronizations, but there is this gap in when we're doing memory traffic of doing the copy. It is actually possible to overlap the copy with the computation. I didn't bother doing that for this plot, but it is in fact possible to do that. Just a little bit trickier on the code side. But then you would get a fully beautiful blue bar. Cool. So now that we've talked a little bit about the high level about how to remove synchronizations and get your pipeline looking good, and you have that beautiful blue bar, the beautiful blue bar does not mean that you're using the GPU well. It just means that you're using the GPU all the time. And so in order to understand if you're using the GPU well, we need to understand more about how the GPU actually works. So what we're going to do is look at the GPU architecture a little bit, and I'm going to do it a little bit high level and simplified, but mostly this is going to explain what's going on. So you can imagine what is a GPU? It has like massively parallel computation. It has lots and lots of threads, like doing lots and lots of computation. And so this is like a picture. We have all these cores that are doing computation, and they have all these registers that they're using to do that computation. And so this seems great, except wait, there's lots of computations that involve like communication between threads. Because like if you're trying to do a reduction where you have like each thread do a little piece of the computation and then reduce the answers to get the final result, well, like they need some way to communicate that. And so actually we have the compute with the registers, and then we also have this shared memory thing, which is memory that can be accessed by multiple threads at the same time, or like multiple threads to communicate with one another. Okay, and so this seems great. You have all of the compute, like lots and lots of threads. You have the registers for doing that computation, and then you have shared memory that allows them to communicate with each other. And this would be amazing if GPUs worked like this, because this is sort of like the fanciful everything is fast world. That's not how it actually looks. Instead, what a GPU has is hundreds of these individual blocks of compute with shared memory. These are called SMs for NVIDIA GPUs, and like an H100 has 132 of these SMs. And the SMs can't really talk to each other. They can, but it's really expensive, and you kind of don't want to ever do it. So you basically want to think about, you have all these SMs, that each can do like sort of lots of good computation, and there's lots of them, so you can do lots of stuff in parallel by splitting among the SMs. And within one SM, you have lots of threads, so you can do lots of sort of parallel computation there. And then they can use shared memory to do some amount of reductions. And so the main thing that you want to do when you're trying to like think about how do you program a GPU is how do you divide up the work of your problem to chunks that each go onto one SM. So you have your big problem, you divide it up into chunks, you assign each SM one chunk. Within that SM, it does some computation, it does some sharing to cooperate between the threads, and then you store that result after you've computed everything back out to memory. And that's the basic flow of how a program on a GPU kernel works. Cool. So there's also these other two things. There's the L2 cache and global memory. So global memory is where all the results are stored and where all the inputs come from. And the L2 cache also like sort of interposes and is a shared thing across all the SMs and interposes to global memory to make things faster. And to give you an idea of like how fast things are, global memory is like 3 terabytes per second on an H100. So like that sounds pretty fast, but it's kind of slow in comparison with like L2 cache with the 7 terabytes per second. And then the shared memory is like 26 terabytes per second. So like if you think about how fast it is to access memory, you really only want to be using shared memory as much as possible. And then like, OK, if you can't use shared memory, then like try to fit it in L2 cache as much as possible. And if you like can't fit it in L2 cache, then like, OK, global memory will be OK. But like for the most part, trying to stay in the higher memory, like layers of the memory hierarchy is like kind of the key component of thinking about how to write an efficient kernel. Like you need to think about, OK, what are the things that I can load in shared memory and do my computation only using those things? And that's the whole thing about chunking up the work is like, what can I fit into shared memory? So when thinking about the performance of a kernel, the two things that you need to think about are like how fast the compute is, like how many matmols can you do or how many like floating point operations can you do, versus like how fast is it to get the memory in from global memory to your like tile of computation. And so those are the two main things that you need to consider. And you think about like how big is your total problem and like how much total computation, or like how big is your tile and how much compute for that tile and how much memory traffic for that tile, and like where's my bottleneck. And there is like actually one other one, which is the kernel overhead. So here we're launching a bunch of kernels. It takes actually some decent time to launch a kernel. It's like 5 to 10 milliseconds on the CPU side. Sorry, 5 to 10 microseconds on the CPU side. And then on the GPU side, there's like usually about a microsecond of gap. So if you're launching kernels that are too small, that take like under a microsecond to execute, well, then you're just like entirely bottlenecked by overhead. And so like those are the two main, those are the three main things that you need to worry about. And you can see here in this plot, we're doing all these CUDA API launches, and then the GPU just like gets completely starved. Like we used to have that beautiful blue bar, and then we started launching these small kernels, and like things are like still mostly blue but getting a little jagged, and then eventually we just like gap, waiting for the CPU to launch kernels. And this like GPU starvation is like, I want you to think about Grommet here. You got to like lay down enough kernels for the GPU to execute before the GPU gets there, otherwise you're going to crash. And we don't want Grommet to be sad and crash. So got to make sure your work is long enough, your rails are long enough for the GPU to continue executing. So I'll hand it over to Savant to talk about these bottlenecks.
So yeah, as Corwin said, we have kind of 3 types of bottlenecks: compute bottleneck, memory bottleneck, and kernel overhead. And fortunately, like there are ways to mitigate all of those. And I'll explain high level what they are, and then we'll dive a little bit more into some of those. For the compute bottleneck, NVIDIA GPUs come with these things called tensor cores, like especially for kernels that are very compute bottleneck, like matmols, where you have to do lots and lots of compute for not that many memory reads. Tensor cores are great because tensor cores are specialized cores on the GPU that do very small tiles of matmols. And this is where like all of the teraflops of training machine learning model come from nowadays. We're not going to dive too much into that because it would take like an hour-long talk, and we don't have another hour to talk about them. But if you're interested, I definitely recommend checking out talks, for instance, talking about flash attention kernels, and how they kind of change the algorithm of the attention to leverage the tensor cores and make sure they use them like 100% of the time. For the memory bottlenecks, the main thing you want to do usually is something called kernel fusion. Basically, if you are bottlenecked in your kernel by loading stuff from memory, you need to do more stuff inside of your kernel. So instead of launching one small kernel that does, I don't know, an addition, and then another small kernel that does a multiplication, like try to fuse those two things together so that you load the memory, do all of your compute, hopefully enough compute to kind of amortize the cost of loading the memory, and then save the results. And this is the thing we're going to look deeper into for the rest of the talk. And then for the kernel overhead, again, kernel fusion can help because if you have less kernels and they do more stuff, you will amortize the cost of that overhead over like more operations. The other thing that can help is a technology called CUDA graphs on NVIDIA GPUs. The idea there is that if you want to launch lots of small kernels, you can record that once and for all. So the first time you do it is still going to be slow and look like the profile trace that Corinne showed earlier. But the second time you replay that graph, and the second time you do the same thing, like it's going to be like everything is going to be stitched together on the GPU because it will have remembered like all the launch parameters that were needed for all of those kernels, so you won't pay that overhead more than once. And so this is a technology that's particularly helpful when you want to launch lots of small kernels and you can't really like fuse them all together for some reason. So yeah, I kind of said the idea at a high level, but let's say we have this string of computation. So let's say we have a particular operation that's often appearing in neural nets called layer norm, and then we want to do like some activation function like a ReLU, and then we want to like add stuff back. This is a skip connection. Again, like all that stuff is like very common in neural nets. And all of those, I've chosen them because like all of those operations are heavily memory bottleneck. Like basically, this is just like element-wise vector operations that you want to do. And so for each of those kernel, you'll spend some time like loading the inputs, doing some compute, and then storing the output just so that you load them again. So like we start with the layer norm. Layer norm like loads inputs and weights. It's going to split them across the SMs that we showed earlier. Each SM is going to do some work, store the results back in the global memory, and then immediately after, we load potentially like the same output from global memory back into our SM to do the ReLU and store the results back to the global output. And then finally, we reload again the inputs that maybe we had loaded previously from global memory into our shared memory to do the addition. And that's kind of inefficient. Like each time you have a red followed by an orange, you kind of want to remove that. Just because that seems pretty inefficient. And like the thing you really want to do is this, like loading memory once, doing all of the operations at once, layer norm, ReLU, and addition, and then store the results back. The problem there is that then you need like an infinite number of kernels. Like each of those operations, layer norm, ReLU, add, this is a kernel that someone hand-coded, and if you want to have like fuse kernel for everything, you basically need to like write those fuse kernel for everything. And you need like kind of infinite number of people coding infinite number of kernels. Fortunately, PyTorch comes with something that helps, which is called torch.compile. So the torch compiler is something that is going to trace what you're doing with your inputs and try to find opportunities for fusions. And it's actually extremely good. Like I chose those layer norm, ReLU, and add because they are more bottleneck operation, but also because that's something that torch.compile is really good at kind of automatically fusing together. So yeah, it's going to analyze. The first time you run a model with torch.compile, it's going to be very slow because it's going to trace what's happening to your inputs and like what operations are done inside of your models to those inputs. And then it's going to try to find opportunities for fusion and run some micro benchmarks to find like, is the fusion here helpful or not? Like, is it making things faster or slower? And once it's run all of that and decided, like you come up with a model with some fused kernel that's going to be much faster the second time you try to use it. One thing to know when you're doing things that use torch.compile is that the PyTorch compiler is becoming better and better, but it doesn't necessarily know everything. And so if you have an operation that's kind of fancy in the middle of your model that PyTorch doesn't know about, it's going to create what we call a graph break. Like PyTorch is not going to try to fuse that operation it doesn't know with anything because it can't do that. It doesn't know it. So it's going to try to fuse things before. It's going to try to fuse things after. But basically, if you have lots of graph breaks, you're kind of removing lots of opportunities for kernel fusion inside of your model, which makes the torch.compile model a bit less efficient. So yeah, kernel fusion, fine. Torch.compile does that automatically for us. Maybe this is the end of the talk, but no. Like sometimes the PyTorch compiler is not good. Oh, you have a question, sorry.
Do you have an example of these like bad operations that might come up?
So there's some like bad examples. Like I think at one point, PyTorch didn't like know how to represent dictionary comprehensions. And so if you had a dictionary comprehension, then it would break the fusion through that dictionary comprehension. And this is just like a pure Python feature, so it should be totally fine, but actually broke the compilation. There's like other things, like if you write a custom kernel and that like you've put that in as a custom operator, then PyTorch is like not gonna know how to fuse that custom kernel that you wrote with the kernels that are happening around it.
And another thing that could happen is that you have an accidental GPU-CPU sync inside of your model that you hadn't detected before. This is also going to create a graph break because PyTorch, the operation is everything that requires synchronizing the CPU and the GPU basically is considered a graph break for the compiler, and it can't fuse that with anything, which is actually a great way to detect if you have CPU-GPU sync in your model. Like try to compile it with the option full graphical true, and it's going to error if you have kind of those hidden synchronization as we had before. And so yeah, sometimes the PyTorch compiler is great and does everything right, and sometimes it's not so great and does everything wrong. And so we do need to like get our hands a bit dirty and like write those custom kernels that are going to fuse a lot of operations. And I'm going to chat a little bit about that for the end of our talk. So the operation I'm going to take an example of is this operation where we want to sum many tensors. Like the actual use case is a researcher wants to log the mean of every gradient in the model because they want to like kind of understand like why the training is not going as they expected. And so to do that, you need to like sum all of the elements in lots of tensors. And this is something that's particularly bad when you want to use your GPUs. In general, like each time you have a for loop and you're programming stuff on the GPU, that is probably extremely bad because like here, for instance, this for loop could be done in parallel because there is no interaction between the various t.sum. And so like we are not leveraging the parallelism of the GPU because the for loop is going to be sequential. And then the other thing that happens is that we kind of are launching lots and lots of very small kernels, and we're back to the picture that Corinne showed before about the kernel overhead problem, where like if we zoom in of why this blue line is like so small, it's basically because our GPU is completely starved. Like the CPU takes 5 microseconds to enqueue a kernel that takes less than a microsecond to execute on the GPU. So basically, we're spending like 20 milliseconds of just having the GPU waiting for some work of the CPU. And this is, so like we have lots of small kernels. PyTorch, torch.compile is great at fusing kernels together. Maybe if we apply torch.compile, it's all going to go away, except not. It's actually a bit worse. The idea is, why is it a bit worse? It's just because when you launch kernels without torch.compile, PyTorch is going to take the absolute best kernel that exists for the operation you want, usually coded by NVIDIA. Whereas the PyTorch compiler relies on some templates of usually written in a language called Triton, which are maybe 80 or 90% of the performance of the best NVIDIA kernel, but not like the most performant thing. And the idea is that it's still going to be faster at the end because you fuse things together, so you will gain way more than what you lose with those templates thing. But when PyTorch is not, the Torch compiler is not really able to fuse things, you actually end up with something that takes a little bit longer. And so that's the case here. Basically, the Torch compiler is not something that's, it's not really a real compiler. Like it's not like saying, oh, this is a for loop. This for loop could happen in parallel. I'm going to create a kernel that's going to do exactly that. It's just like it's tracing what's happening to your inputs. So like it sees the for loop completely unrolled, and it's not able to like, yeah, it's going to fuse things here and there inside of that for loop, but it's not able to do that thing very efficiently. So this is a situation where we actually need to write a custom kernel to go way faster. We'll see at the end of the talk how much faster we get with that. So yeah, when we want to write a custom kernel, the first question that we need to ask ourselves is, how do I split the work between my SMs? So Corinne went over the GPU architecture a little bit earlier. We have some compute and shared memory grouped in those streaming multiprocessors, and each of them cannot talk to the other. So you need to split the work in independent chunks. So here for our problem, it's very easy because we have lots of tensors. Computing the sum of individual tensors are problems where you don't need to talk to each other. So like we can just assign one tensor to one SM. You might think like there's a problem. We have 132 SMs on an H100, and we have like thousands of tensors because this is a very big model that has like lots of layers. That's actually not that problematic because when you assign work on the SM, it's very dynamic. So like as soon as one SM is finished, it's going to like request more work and it's going to be assigned a new tensor. And even if like our tensor shapes are kind of different, it's going to be even. It's going to even out in the long term. Like for instance, here SM2 is probably going to be done before all the other SMs because it has a smaller tensor. So it's going to like be the first one to request more work. Maybe the next work will be a bigger tensor. Maybe it's going to be another small tensor again. But like if it just keeps getting small tensors, it will do more work than it will like compute the sum of more tensors than the other SMs. And so in the grand scheme of things, it's just going to be fine. So yeah, we split our work this way, one tensor per SM, and then inside of each SM, we also have lots of parallelism. So we need to like compute the sum of one tensor on an SM using that parallelism, using those mini cores that we have on each of the SM. So like here, it's just the idea of this is a sum. Sum has a very parallel implementation, which is just like we kind of take each thread and assign them, like we're going to compute partial sums, and then we're going to reduce the partial sums together using the shared memory. One thing we need to worry about is that we can't just say like thread 1 is going to take the first 4 elements and then thread 2 the next 4 elements, just because we want threads to be loading data that is sits next to each other. This is just an optimization because on GPUs, if each thread wants to read things that are consecutive in memory, they'll be able to do a much wider load together. That's going to go much faster. So that's why we split this work, the work this way, and not like saying just compute the sum of the first 4 elements, for instance. And this is assuming we have a thread in the picture because I was lazy, but in actuality, we'll have like 10, 24 threads on each SM, for instance. And so once each thread has computed the partial sums, we use the shared memory and we can like reduce until like, for instance, like the first thread has the final result, and then this third thread will store that final result into the global memory where we wanted the result. Looking briefly at code, I know it's been a long talk and you're a bit tired, but like let's just look like some big blocks of how we would code this. So the custom kernel, you need to go to like the language in which we program GPUs, which is called CUDA, and which is a variant of C++. So writing a custom kernel looks like this. You have a function that is executed on the CPU that launches the kernel. So here it's called like some mini kernel. And when you launch it, you say how many blocks you want. That's going to be like how many SMs. And then in each block, how many threads you want. So like here, we request 10, 24 threads in each block, and we launch like 1 block per tensor because we said like we would split the work, giving 1 tensor to 1 SM. Then the some mini kernel is going to look like this, roughly. The first thing is finding out who you are. Like every thread on the GPU is going to execute the exact same code, so we just need to make sure that they specialize to like the particular tensor they're supposed to be taking the sum of. And we have this global constant called block IDX, which tells us which SM we are. So by basically taking the value of this constant, we can know, oh, I'm supposed to compute like the sum of this particular tensor. And then this is the loop where each thread computes partial sums. So each thread begins at its thread IDX. So thread IDX is the same thing as block IDX, except it tells you like which thread you are among like the 1024 thread of the block. So like thread 0 begins at 0 and then goes to like the element 1024, while thread 1 begins at 1 and then goes to the element 1025, and so forth. And so this for loop computes the partial sums. And then we have like to reduce all of those partial sums together to compute the final result. I'll go over that in a minute. And finally, the thread number 0 will store the final result at the right place in the output. And again, to find like what is the right place in the output, we use this block IDX, which tells us for which tensor we're responsible of computing the sum. And yeah, the sum block function, going roughly over this, is, oh, we talked about that, okay. I forgot this part. So the sum block function is going to use another thing called warps. One thing we didn't tell you about is that the code on the GPU is going to be executed like not all the threads are executing in locksteps. They are executing in lockstep by groups called warps. So 32 threads, that's why warp size is 32 at the top. 32 threads always execute everything in locksteps. And inside of the warp, we have like some way to share things even faster than shared memory. We don't even need to go to shared memory. Inside a warp, we can just use registers to share values. So that's why like this distinction here is important. So from our 10, we requested like a block of size 1024, so we have 32 warps of 32 threads. So we can then compute like what's my warp index and what index I have inside of the warp. We have our shared memory where we're going to store all the partial results. And the way we do this is we only store the partial results for 42, the number of warps, 42, like not the partial results for all of the threads, because we can use those warp reduce things that are much faster. And so that's, this way we only have like to store like num warps partial sums. So we do that, and then we store like lane index 0, so the thread index 0 inside the warp will store the results in the shared memory. And very importantly, we need to synchronize everyone to make sure that since different warps don't necessarily execute in lockstep, they might arrive at this line at different times, and we want to make sure that everyone is here before we continue, because we want to make sure that everyone sees the same shared memory before we continue. And then, if we are the warp index 0, we do one final warp reduce, because since our thread block size 1024 was 32 by 42, we have 32 values to reduce, which is exactly the size of a warp, so we can just use another warp reduce to do the final warp reduction. And if we're not warp 0, we just return something. We don't care because if you remember the code on the previous slide, only thread index 0 is going to store the results, so only thread index 0 needs to have the right results returned to it. So yeah, that was a lot of content, but the main result is that it used to take like 20 milliseconds to do that sum of lots of tensors, and with the custom kernel that takes a week to write if you're new, an afternoon to write if you're more experienced, you get that time down to 30 microseconds, so almost like 1,000 times faster. So it's definitely worth learning how to, sometimes go deeper into what the GPU programming looks like. More questions? Yeah.
When you're writing custom kernels at Jane Street, how often do you write like CUDA C++ directly, or something higher level or lower level like PTX?
Yeah, so that's a great question. So first thing, we try not to go deep at all. Like if we can, we express the computation in pure PyTorch, like maybe vectorizing the code a little bit better, maybe like accessing some function that can do some stuff for us a bit better, we do that. And then the next thing we try is usually Triton, which is DSL in Python, that gives you a higher level it's a higher level language to program the GPU, but doesn't give you access to all of the features of the hardware. So usually, if you can code things there, but like usually you will maybe have access to 80 to 90% of the performance of the GPU. And then when you either like because our kernel is not suited at all to Triton and we can't write it here, or because we want the absolute best performance, we'll reach deeper into CUDA. We don't write a lot of PTX. Sometimes you have a CUDA kernel and like you need to like inject a particular PTX instruction because you really want the compiler to do that. But we don't like write the whole kernel in PTX.